1 billion AI brains, 250 gigawatts of computing. The real challenge for Tesla is no longer building the body of Optimus, it is building enough intelligence to power millions of them. Elon Musk estimates that roughly 25% of Terafab's future AI capacity could eventually be directed toward Optimus, theoretically providing enough computing capacity for around 1 billion AI brains based on the AI5 benchmark. But why would a humanoid robot need this much computing power in the first place? Consider the scale. If Tesla eventually puts 10 million humanoid robots into the real world and each robot requires an AI system capable of drawing up to 800 watts under peak computational demand, the theoretical requirement would reach approximately 8 gigawatts if every robot operated at maximum computational load simultaneously. That does not mean Tesla would need to generate 8 gigawatts continuously because millions of robots would not all operate at peak AI demand at the same time. But the calculation exposes the infrastructure problem hiding underneath Optimus. A million intelligent machines are not simply a million mechanical products. They are a million computers interacting with the physical world. And this changes the economics of robotics. A traditional robot can be designed around a narrow task, welding a specific component, moving a box along a fixed route, or repeating the same motion thousands of times. The computing requirement can therefore be relatively predictable. Optimus is being designed for a much broader range of environments. It may eventually need to pick up unfamiliar objects, navigate changing spaces, recognize humans, interpret instructions, manipulate delicate items, and respond when something goes wrong. Every increase in capability creates another layer of computational demand. The robot becomes more useful only as its AI becomes more capable. That is where AI5 becomes critical. The figures used in this analysis put Tesla's next-generation AI5 at roughly 2,500 trillion operations per second, compared with approximately 100 to 150 trillion for the current Tesla generation. The chip is also described with 192 gigabytes of memory and up to 1.5 terabytes per second of data movement. Whether every final production specification matches these projections remains to be seen, but the direction is clear. Tesla is pursuing a much larger computational platform rather than simply making a slightly faster version of its current hardware. The important point is that raw computing power matters because Optimus has to process several kinds of information simultaneously. Its cameras provide visual information. Other sensors provide information about movement, position, force, and contact. The AI system has to combine those inputs, interpret the environment, decide what action makes sense, and then translate that decision into precise commands for the robot's motors and hands. These processes cannot simply happen one after another with long delays between them. The robot has to perceive and act as one continuous loop. This becomes especially obvious when considering a highly demanding environment such as surgery. A future humanoid robot operating in a surgical environment would theoretically have to process high-resolution or 3D visual information, track instruments, distinguish healthy and damaged tissue, monitor vital signs such as heart rate, blood pressure, and oxygen levels, interpret sensor feedback, and continuously adjust its physical movements. This is not evidence that Optimus can currently perform autonomous surgery, and medical applications would require enormous advances in safety, validation, regulation, and reliability. But as a computational stress test, the scenario reveals exactly why physical AI is different from ordinary software. In a data center, an AI model can process information without directly controlling a moving body. A humanoid robot does not have that luxury. Its decisions immediately affect the physical world. If Optimus reaches for an object and the object moves, the robot must update its understanding. If its hand encounters unexpected resistance, it must adjust its grip. If a person suddenly walks into its path, it must recognize the change and modify its movement. If the robot loses balance, perception, prediction, and motor control have to work together almost instantly. The intelligence is not sitting behind the machine, the intelligence is controlling the machine. That is why the difference between 100 to 150 trillion operations per second and roughly 2,500 trillion is potentially more important for Optimus than it would be for a simple industrial machine. More computing headroom gives Tesla more room to run larger models, process more sensor information, and perform more complex tasks without forcing the robot to sacrifice responsiveness. The goal is not simply to make Optimus calculate faster. The goal is to make the robot capable of handling situations that cannot be completely predicted in advance. But even the most powerful AI chip is useless if Tesla cannot produce enough of them. This is where the problem becomes much larger than chip performance. Imagine Tesla succeeds in building a factory capable of producing millions of Optimus units every year. Every robot would require an AI processor, memory, power delivery, thermal management, sensors, communications hardware, and the semiconductor packaging necessary to integrate all of those components. If chip production cannot scale at the same rate as robot production, the semiconductor supply chain becomes the bottleneck. This is the problem Terafab could be designed to solve. Instead of treating AI computing as a component Tesla simply purchases from the market, Musk is pursuing dedicated semiconductor infrastructure capable of producing enormous quantities of AI compute. Under the scenario outlined by Musk, if approximately 25% of Terafab's capacity were allocated to Optimus, that could represent around 250 gigawatts of AI computing capacity per year. Using AI5 as the reference point produces the theoretical estimate of roughly 1 billion Optimus-class AI brains annually. That should not be interpreted as Tesla officially promising to manufacture 1 billion physical robots every year. It is a scale calculation showing how much computing infrastructure Musk's vision could potentially support. And this is where AI5's recent development milestone becomes important. Elon Musk has publicly congratulated the Tesla AI chip design team on X for taping out AI5. Tape-out is a significant transition because it means the design has reached a stage where it can move toward physical fabrication. Samsung Foundry has also said that the Tesla AI5 chip is planned for production at its Taylor, Texas facility using a 2-nanometer class process. Mass production is still a separate milestone, but Tesla is no longer discussing AI5 purely as a distant concept. The company is moving toward turning the design into physical silicon. Tesla's claimed economics are equally important. The current figures being used in this analysis suggest that AI5 could eventually deliver up to 50 times the performance of AI4 at around 10% of comparable NVIDIA cost. Those figures should be treated as Tesla's target or claim rather than an independently verified production benchmark, but if the economics were achieved, the strategic implication would be enormous. Tesla would not merely have a more powerful AI processor. It could have a pathway toward making advanced AI compute cheap enough to deploy inside millions of physical machines. That distinction matters because NVIDIA's economics demonstrate how valuable advanced AI compute has already become. NVIDIA's data center business generated approximately $75.2 billion in quarterly revenue, up 92% year-over-year in the period referenced here. The conventional AI industry concentrates enormous amounts of computing power inside data centers. Tesla's proposed strategy is almost the opposite. It wants to push computing power outward, embedding AI directly into cars, robots, and other physical machines. If that strategy works, every Optimus becomes more than a robot. It becomes a physical AI endpoint. It can receive information from the real world, process it locally, make a decision, and act on that decision through its mechanical body. Multiply that architecture by 1 million robots, and Tesla would effectively have 1 million physical AI systems operating simultaneously. Multiply it by 10 million and the scale becomes difficult to compare with today's robotics industry. This is also why Tesla cannot afford to think about Optimus as only a mechanical manufacturing problem. The company needs the robot body, but it also needs the brain. It needs actuators and batteries, but it also needs processors and memory. It needs factories for the physical machines, but it also needs semiconductor capacity for the intelligence inside them. The entire system has to scale together. What does Optimus actually need a brain that powerful for? The answer becomes clearer when Optimus is placed in an environment where simply recognizing objects is no longer enough. Imagine a future surgical scenario. A humanoid robot would have to interpret a 3D endoscopic view while tracking the exact position of surgical instruments and surrounding tissue. At the same time, it would need to monitor the patient's heart rate, blood pressure, and blood oxygen levels, recognize changes in tissue, interpret feedback from its hands, and continuously adjust its movements. The challenge is not performing any one of these tasks individually. The challenge is performing all of them simultaneously while maintaining a complete understanding of what is happening. That is fundamentally different from the work performed by most industrial robots today. A factory robot can repeatedly move an object from one position to another because its environment is highly controlled. Optimus is being developed for a much less predictable world. Objects can move, people can suddenly appear, surfaces can change, and the robot may encounter situations it has never seen before. Instead of simply following a fixed sequence, it has to constantly evaluate the environment and determine what action should come next. This creates a critical distinction. Physical intelligence is not just about recognizing what something is, it is about understanding what that information means for the next physical action. If Optimus sees a glass on a table, recognition is only the beginning. It has to determine where the glass is, estimate how to approach it, calculate the appropriate grip, coordinate its arm and hand, and adjust instantly if the glass starts to move or slip. Vision, spatial reasoning, prediction, and motor control must function as one continuous system. Now introduce another variable. Suppose a person suddenly reaches toward the same object while Optimus is moving its hand. The robot cannot simply continue executing its original command. It has to recognize the new movement, determine whether it creates a potential collision, change its trajectory, and maintain control of its original task. Every unexpected event creates another decision that has to be made inside a moving physical system. And this is where AI5 becomes important without simply repeating its specifications. Its value is not just that it can process information faster. Its real purpose is to give Optimus enough computational headroom to handle multiple complex processes simultaneously. The robot has to understand what it sees, combine that information with sensor feedback, predict what may happen next, and translate the result into precise physical movement. That changes how Optimus should ultimately be measured. The number of tasks it can perform is only one metric. A much more important question is what happens when conditions change unexpectedly. Can it recover when an object moves? Can it adjust its grip when resistance changes? Can it recognize that a person has entered its path? Can it modify its plan without losing control of everything else happening around it? That is the difference between a programmed machine and genuine physical intelligence. Tesla is therefore not simply trying to build a robot that can perform more tasks. It is trying to create a machine that can understand unfamiliar situations and decide what to do next. The more environments Optimus enters, the more variables it must process, and the more important its computational capability becomes. So the real question is no longer how many tasks Optimus can perform. It is how much complexity Optimus can handle before intelligence itself becomes the bottleneck.